Hello, welcome to CE 366 Geotechnical Engineering 1. Lecture 1. This lecture is talk about the soil relationships, particularly in the phase relationships. And the learning objectives for this lecture is to understand and able to solve soil phase problems. So what is soil? If you look up to a soil wall, or like you have some soil samples you collect from the ground. Soil part You realize soil is a collection of many different particles, and those particles could be solids like sand particles, or some like a cohesive material, and actually those are clay minerals. And the within the particles or minerals, a soil matrix could be filled with different type of fluid, which is water. So sometimes you have some moisture, you feel some moisture in your hand when you touch on the soils. Those are because you have water or other kind of fluid within the soils. And you could be very likely if you above the groundwater tables, you also find air pockets and also gas if you look carefully enough. And in our geotechnical world, there's two major classifications of soils. One is sand, the other is clay. And for practice purpose, very likely we further classify our soil according to geological formations or geological settings. And in Southern California, you would imagine our soil layers or the soil profile, or if you go deep into the ground, you will come up with different type of formations. So this could be your ground surface, and all the way deep down you have your bedrock. And in an overall picture, uh, is according to the geological formations in Southern California, right above the bedrock, you will have the San Pedro formations, and above it, you have the liquid formations, and above it, you have a softer materials, the alluvial soils, which make up with the young alluvial soils on top of the old alluvial soils. And on top of that could be artificial fill. So the formations of those geological settings is based on geological times, and soils layers usually is formed by sedimentations. So throughout the geological times, we talk about like hundreds to thousands of years. Each layers of a soil layer is formed, and obviously like the youngest layers on tops and the oldest formations at the bottoms. So right before right on top of the bedrock, you can imagine it's like the San Pedro formation is the oldest formations, and the behavior and the strength wise is very like rock type materials, and the top that you go, then the weaker the soil could be. So those are the overall uh, picture of what geotechnical engineers deal with. They uh, we are a branch of engineers that we're also very work closely with the geologists. So what is soil? What is soil? Again, soil is a collection of particles, and the picture over here on the right hand side pretty much give a good descriptions on or visualizations on what you may have when you have soil samples. Your collections of different soil particles, so represented by all these dots here. So those could be solids like sand. You know, if you go to the beach, you play with the sand particles, or it could be minerals, or when you have a clay specimens, and in between those particles or minerals, there's a void. And the void could be either filled with fluid or filled with air or gas. So there's like a different phase over there. So this lecture is about phase relationships. So throughout this lecture, we will do basic calculations. So at the end of this lecture, the expectations is the students can do basic calculations to find out the weight and volume relationship between those phase. So the phase are the solid phase, the water phase, and the air phase. And whereas the solid, air, and water come from, we could like visualize that like with a picture like this. And in between excuse me, and in between the salt particles, in general, there's like a have a very weak cementations between them. If there's a very strong cementations, they will become like a walk type of material instead of a. Okay, so we have learned the soil matrix is made up of air, water, and solid. And for the void, the one that occupied by the air and water, and the void is between all the soil particles. So again, like if we look at this picture here, is in between all those soil particles, all the space over there is a void, and void can be occupied either by air or by water. And to learn this, like our phase relations, we need the phase diagram. So the purpose of the phase diagram is for us to quantify, given the soil samples, how much soil solids, soil air, and soil water right there. And the way that we quantify it is we look at both the weight and also the volumes. So phase diagram we can further develop into two categories. When we talk about the phase diagram, it is a link or like a diagram. The main purpose is to linking between the weight and also the volume. So we want to know about the weight of the volume of each of the three different components, air, water, and solids. And for this, like a C366 class, the first couple of weeks were important is for us to pick up all the terminology. So lecture ones, there's a bunch of different like new terms for us to learn in order to speak the geotechnical language. So the set of terminology is from the phase diagram. So within the phase diagram, um, we have the weight and also we have the volumes. And very important, the purpose of the phase diagrams is try to link the informations between the weight and the volumes. And between like each phase, the weight and volumes, we need to look at the air, water, and solid. And for the volume part, the first terminology we talk about is the volume of air, very likely. Also, we have the volume of water, and also we have the volume of solid. And we want to quantify each of them based on the measurements that we can make into the field or in the lab. So this lecture one, the phase relationships, is try to is what we try to talk about is try to find the numbers, try to calculate all those terms right there. Volume air, volume water, and volume solid. And like the picture that we look at it together, in between the solid particles, those are the void. And the void can be occupied by the air or water. And so that's why when the volume of the air and water, when they add up, you have the volume of void. So volume of void is equals to the volume of air plus the volume of water. And when we make up all this like three terms right there, we have the total volumes. We have the total volumes. So the total volumes will be equals to the volume of air plus the volume of water plus the volume of solid. So that is the volume part. And on the right hand side or the other side of the phase diagram, we have the weight components. And similarly, we have the weight of the air, we have the weight of water, and also the weight of solid. And realize that the weight of the solid actually, the weight of the air is small enough that we can claim this is zero. So the weight of the air is not significant. It's negligible. So that's why the weight of the air oftentimes, or at least like in this class, we can always state that the weight of the air is equal to zero. And when we add up those three terms, we have the total weight. So the total weight will be equals to weight of water plus the weight of the solid. And oftentimes, the weight can be either mixed with the mass. Sometimes like we use mass to represent the weight. And actually, they are the same thing because the weight is equals to the mass times the gravities. So the difference between the weight and the mass is the constant, which is the gravity. So sometimes, like you may see problems that represent the weight by pounds. So weight usually come with pounds or kilonewtons. If it's an SI unit, it could be kilonewtons. Or mass usually is represented by grams. So sometimes you have the mass of the air, which is also equal to zero. The mass of the water, or the mass of the solid, and also the total mass. So realize that the mass and the weight essentially they are the same thing, but the difference is just by a constant of gravity. So we learn about this phase diagram. A phase diagram is very important. One more times, is used to link or try to relate the informations between the volume and weight. So when we talk about the volumes, it means all these components: volume of air, volume of water, volume of solid. And when we talk about the weight, is the weight of the air, which is equal to zero, the weight of water, and also the weight of the solid. And for the learning objective for this lecture is for us to able to calculate all these terms for this given informations. So we get there and we see some example problems. You will see, like when you're given some informations, very likely is some measurements from the field or measurement from the lab or of our source samples, and based on those measurements, could be the total unit weight, or could be like a total mass, or could be a water content. Based on those measurements, how to back calculate each of these terms. So this is the main goals for this lecture, knowing how to find out all this component to form phase diagram. And when we talk about phase diagram, the first thing I want you to think of is both the volume and the weight, and realize that the phase diagram is to be used to link the informations between the two. So one more final point about this slide, and then we move on. We talk about the weight of the air is equal to zero, but how about the volume of air is volume of air equal to 0, like the rate of the air? The answer is it depends. So volume of air is not equal to 0 when the saturations of the void is not equal to 1. So saturation means water saturations. So you imagine that the volume of air will be equal to 0 when your soil specimens, which can be represented by this phase diagram over here, when the saturations of void is equals to 100%, which means when you have 100% saturations, means all the void now is occupied by water, and there's no air. In that case, then the volume of air is equal to 0. If the questions didn't tell you it is 100% saturated, or it didn't tell you anything about saturated, that means there's air. Okay, more terminology to follow. So now, on top of those like components from the rate and the volumes, now another terms called void ratios. So the definitions of void ratios is equals to the volume of a void divided by the volume of solid. So volume of void is the volume of the air plus the volume of the water. Um, when that normalized by the volume of solid, that gives you the void ratios. And the typical range for the void ratios is between 0.5 to zero point 0.2. So those are common soils. And the other terms related to that is porosity. So porosity is similar to the void ratios, but now the volume of void is being normalized by the total volume. So this is the porosity. Porosity is come with a symbol N. And the typical range for porosity is between 0.9 and 0.2. The geotechnical engineers like to use void ratios to represent the density or the volume of void. That's the geotechnical applications. For transportation engineering, they more prefer the terminology of porosity when you come to void and density. So it highly depends on the applications because very likely like geotech engineers many times they need to reference to the volume of solid. So it's more like a material base. But like for transportations applications, more likely in more cases they need to reference to the total volumes. So they will use porosity more often than we do. But in fact, both the void ratios and the porosity, they are related with each other. So we can prove the relationship between the void ratios and porosity. So start with the void ratios. The definition of it is one more times, the volume of void divided by volume of solid. And we know that the volume of solid is the total volumes minus the volume of void. And if we do our math, we try to normalize both the top and bottom with the total volumes. We got this formula. And in fact, the terms here now, volume of void divided by the total volume on top, it is the definitions of porosity. So we got this relations. Now is the void ratios equals to the porosity divided by 1 minus porosity. And if we do our math, The porosity is also can be represented by the void ratios. So more terminology to comes now is related to water. So the previous one that we just talked about, both the void ratios and porosity, pretty much is related to the void. And now we talk about the water part. We talk about the terminology for the saturations and also water content. So the definitions of saturations is equals to the volume of water divided by volume of void. So we try to represent how much void is occupied by the water in terms of volumes. So you imagine if all the void is occupied by water, then you will have 100% saturations. So this is fully saturated. When your volume of water is equals to volume of void, because now all the void is occupied by the water. And the other extreme case is you have 0% saturations, which means your soil samples is often dried. Very unlikely, it's almost impossible. It happens in the field. But like, if you collect the soil samples, you bring it to the lab and you put your soil samples in the oven, you keep it at a temperature of 100 degrees Celsius for 24 hours. Now, your soil sample is often dry, which means all your water is gone. So the volume of water is equal to zero. Then you have 0% saturations. Okay, next, water content. So water content is equals to the weight of water reference to the weight of the solid. So that is the water content. And we understand that the weight, we talked about this in a couple slides ago. The weight pretty much is equals to the mass times the gravity, right? So which means like the water content is can also calculate by the mass. Either weight of the mass, we get the same thing because the gravity terms cancel out. And then times 100%, that gives you the water content. Or same as the saturations here is usually represented by percentage. So we multiply the 100% there. So that is the water content, which is the weight of the water divided by the weight of the solid. And typically, the water content, if you think about it, is less than 100% because very unlikely you have more water in terms of weight than the solid. So for common soils, you have water content very likely less than 100%, and the typical range is maybe about like a couple percent to like a 30 or 40%. If you have 40% of water content, that's pretty high already for common soil. For clay soils, you can even go higher to maybe 60%, still being like feasible. But for common soils, where unlikely you will go over 100% for the water content, unless you have special soil like organic soil. When you have organic soils for your site, be very careful because organic soil is very soft, and this is usually the problematic soils that you want to stay away from, or like if you can get rid of it, you want to get rid of it, which means you excavate out. But if you have too much of them, then it's become too expensive to relocate or too expensive to excavate to get rid of all the organic soils, then you may need to do a ground improvement. And organic soils, you can be identified by the smells or the trace of organic matter, and also it can be identified by the water content. Because if you have organic soils, the organic matters usually can hold up a lot of water, and end up you have a water content that can go up to 200%. All right, more terminologies to come. This time, so we look at the density. So first, we look at that total density. So total density means the mass, the total mass divided by the total volumes. So density can also be either mixed with or can also think of like the other way is the unit weight. So unit weight is gamma T. So the total unit weight is gamma T is equals to total weight divided by the total volumes. And don't be confused between density and unit weight. So density, the definition is mass over volume. And unit weight, the definition is the weight divided by the volume. So again, it's like a mass and weight is a matter of or different of a constant of gravity. So given the phase problems, sometimes like they ask you about density, sometimes they ask you about unit weight. You just need to be very careful on which one is from the mass and which one is from the weight. And mass again is usually represented by grams, and weight is usually represented by pounds or kilonewtons. So that is the total density. And also there's a dry density or dry unit weight. So the dry density is equals to the mass of the solid divided by the total volumes. And you have the dry unit weight, gamma D. There will be the weight of the solid divided by the total volumes. So a few weeks later, when we get to the topic compactions, I believe that is topic number 7, if I'm correct. Then we talk about where we focus we put a lot of time on this like dry unit weight gamma D. Next is the density of solid. So density of solids is the rho s here is represented by defined by the mass of the solid divided by the volume of solid. And similarly, the unit weight of solid will be equals to the weight of the solid divided by the volume of solid. And one like popular correlations or relations between we want to like relate to each other is the total unit weight and the dry unit weight. And we want to try to relate the two. So the total unit weight is equals to the total weight divided by total volumes, and which is equals to the weight of solid plus the weight of water divided by the total volumes. And in fact, the weight of the water can be represented by the water content times the weight of the solid divided by the total unit weight, sorry, the total volumes. So if we do our math here, we factor out the weight of solid, then we have 1 plus the water content divided by total volumes. And in fact, this term here, the weight of solid divided by the total volume, that gives you the dry unit weight. And if we do our math, the total unit weight will be equals to the dry unit weight times 1 plus the water content. Oops. So that's the terminology for the density. Okay, furthermore, so this slide number 9, I would say this is a very important slide. So if you understand this slide, then very likely you understand this topic, the phase relations. So the purpose of this slide is we want to try to represent, kind of also like a mental exercise for us to recap what we have learned here. So given a phase diagram, remember like that this phase relations problems, everything starts from the phase diagram. And given the phase diagram, we have learned all this terminology now. Um, on top of those like a volume and weight of each of the air, water, and solid components. We also learn about this terminology on the water ratios, the saturations, um, the unit weight of water, and also the volume of void, all this concept. And we want to make use of this terminology to represent the phase diagram. That's what we try to do. And one more time, very important is for the phase diagram is the main purpose is to link the informations between the weight and the volumes of a given soil samples. And we know that the weight of air is equal to 0. So just take care of one thing first. And in order to link between the weight and the volumes, I always want you to remember this. Remind yourself when you need to solve for a phase uh, relations problems. Remind yourself you have two bridge to link the volumes and also the weight of all the soil phases. So the very first hints or very first important piece of information is the unit weight of the water. The unit weight of water. So this is powerful because the unit weight of water is equals to 62.4 pound per cubic feet or 9.81 kilonewtons per meter cubes. So this is kind of like a free information because this is just a constant that we can always use. And this constant provides you the bridge between the weight of the water and the volume of water. So this become powerful because uh, uh, the whole purpose for phase relations is try to fill up all the informations for the three different phases, both the volume of each of the air, water, and solid. Now, which tells you once look at this equation here. Now, what just tells you either you know the rate of the water or the volume of water, then you can find out the other one because you know the constant gamma W over there. So this gamma W is very important. The other very useful information is the G sub S, the uh, specific gravity of solid, the G sub S. So G sub S by definitions is equals to the unit weight of solid reference to the unit weight of water. So pretty much once you know the G sub S, then you can relate that with the other terms that we want to find out. Because a G sub S is given, and the unit weight of water is a constant, and the unit weight of solid is the weight of solid divided by the volume of the solid. So now, which means this from these equations is once you know G sub S times gamma W, then you can relate the weight of solid and volume of solid. Either you know the weight of solid, then you can find out the volume of solid, or you know the volume of solid, then you can find out the weight of the solid by knowing G sub S. So those two is a very important piece of informations that will help you to solve phase relationship problems. So back to the goal of this slide. The goal of this slide is knowing all this background and knowing those like bridges for us to solve the problems. Now is kind of like an exercise that now we have the phase diagram. You want to represent this phase diagram with the new terminology that we just learned. And to start, we will start with the volume of solid. We will assume the volume of solids equals to 1. And realize that this is like a kind of like a clever way to do it. It's because the phase diagram is kind of like a scale, which means like all the terms right there, volume of solid, volume of water, and reach of air, all these components right there. It's just like a scale. So you've kind of like a ratios like a respect with each other. So the scale is up to you if the volume is not given, which means like, you got like a portions of one with one of the terms, the other term is relative to the one that you assumes. So if the volume is not given for the case, if you are smart, then you would assume the volume of solid equal 1. So you can always do this for phase problems when there's like a no volume information is given. So if the informations of volume is not given, the smart way to do it is assume the V sub S, the volume of solid, is equals to 1. It could be 1 like a cubic feet, you can be 1 like a meter cube. So it's up to you, because now, like, you're not bounded by, you're not fixed by the volumes. Now just everything is just a scale. So it's up to you. Assume whatever you want, and the easiest way to start is assume the volume of solid equals to 1. You can assume 0.5, you can assume 0.2, you can assume 1,000, but you will want to pick something easy. You want to pick V sub S equals to 1. So you assume the V sub S equals to 1 now, and then now remember we want to represent the phase diagram with some terminology that we learned, which means like also the void ratios. And now, like, I think about what is the definitions of a void ratios. So void ratios is equals to the volume of void divided by the volume of solid. And since we assume the volume of solid is equals to 1, so this is volume of void, then based on the assumptions, we find out the volume of void is equals to the void ratios. So this will be the void ratio. Next, remember, like, we also talk about saturations. So the definition of saturations is the volume of water divided by the volume of void. And we just find out the volume of void is the void ratios. So now we can find out the volume of water, in fact, is the saturations times the void ratios. So saturations, previously I just say there's a simple S, so I need to be consistent. So the saturations is S times E. So the volume of water now is S times E, the saturations times the void ratios. And the total volumes, you can also visualize that like on this graph, is 1 plus the void ratio. This gives you the total volumes. So we are getting there. So the purpose here now is try to represent the both the whole phase diagram with the terminology that we have learned. And for your problem solving problem for like assignment one and for this lecture, this is two periodicals, but that's okay. If you can like understand this slide, that means you are more than ready for solving the homework problems and exam problems. And when we move on to the later part of the semester, when we come back to the compaction, the topic of compactions, solve compactions, all this like a periodicals like concepts we will come back to help you to understand the soil behavior. But hang on there, understand that like what we're doing here now is kind of like an exercise for us to represent a phase diagram with the terminology that we just learned. And we are almost there because we finished the volume part already. So that's two more parts remains here, which is the weight of the water and the weight of the solid. So the weight of the water, remember like at the beginning, we talk about the good uh, bridge or the good like equations or the good relations like can help us to solve for like this type of problems is because like once you know the either the volumes or the weight of the water. Once you know either one, you can always find out the other one. Now the case is we know uh, the volume of water. So we know the volume of water and the weight of the water will be just becomes the unit weight of water times the volume of the water. And the other one here, very similar. We make use of these equations right there. It's because we know the volume of solid, then we can find out the weight of the solid. And in this case, the weight of the solid is equals to 1. So the weight of the solid now is equals to G sub S times gamma W. So this gives us the whole picture of all these terms. Let's have done what we want to do. We want to represent the whole phase diagram with new terminologies that we have learned. Okay, so this slide summarize what we have learned so far. On the left-hand side, we started with the phase diagram, and then we talk about for each of the uh, different like components like from the volumes and the rates and in terms of gas, water, and solids, the VA, VWVS, and the total weight and total volumes. So all those terms are the one that we want to find out, and we'll work on examples like at the end of this lecture, and hopefully give you an ideas on how to from given informations to find out those like a particular uh, parameters. And on the right-hand side on this slide is what we have just did. So we try to represent a phase diagram with the new terminology that we learned in this lecture. The void ratios, the saturations, and the specific gravities, and also the unit weight of water. So particularly we talk about like at this point the weight of the water. The previous slide we end up with the gamma W times the volume of water, and the volume of water is further equals to the saturations times the void ratios. So end up like we have the weight of water can be represented by the unit weight of water times saturations times the void ratios. And likewise, we did the last slides too. If we assume the solid equals to 1, the volume of solid equal to 1, then the weight of the solids will be equals to G sub S times the unit weight of water. So highly recommend you guys uh, to practice this, take out a blank sheet of paper, start by drawing a phase diagram, and then end up to see if you can represent all the components, all the parameters within the phase diagram by those terminology, including the water ratios, saturations, unit weight of water, specific gravity, and also the volume of void. Okay, so before we start doing examples on solving phase relations problems, let's talk about the procedure. Because in the next slide we will start working on examples. But before we work on those real number, I want to emphasize on how to tackle those type of problems. Be very sure that be very clear that. The only way to solve a phase relations problems is through understanding and understand how the phase diagram to operate. That's very important. Rather than try to find the right formula from the book and or maybe try to memorize a formula from the exams for the day before the exams, and hopefully that formula can help you to solve a particular parameter that the problem asks for. Could be saturations, could be unit weight, could be dry unit weight. That's not the way to go. But instead, we should try to put the effort on try to understand how to set up the problems. And hopefully, on this slide, the procedure we have here will set up a good guidelines. So very first step to do is always when you see a phase problems in geotechnical engineering. Very first step, draw a picture. Just draw a phase diagram. That's your very first step. And the phase diagram comes with three parts: the air, the water, and the solid. So that's step number one. That's step number one. And step number two will be fill in the provided informations. So for example, when you're given a questions, like the one that we will work on next, it tells you have a laboratory sand samples from the inside a mold, which is 40 cubic inches. So that gives you the total volumes. And then you took 2.8 pounds of the wet sand, so that gives you the total weight. So whatever the information is given to you, the second step is to fill up the informations. Could be the total volumes, could be the weight of water. So that's the second step. And that's one information you can always fill in, right? Because we talked about this a couple slides ago. The weight of the air is equal to 0. So this part you can fill in. You can fill in. So this part, second step, you can fill up the weight of the air, and you can fill up the volume of air equal to 0. But there's a big if. If saturations equals to 100%. Only if the problem tells you. If the problem didn't tell you anything about saturations, then you cannot assume. You cannot assume the volume of air equal to 0. Also, on this a step, what you can also do is you can assume the volume of solids equals to 1 if no informations about volume is given. So we talk about this because the phase diagram is like a scale. If the volume is not fixed, then that the scale is up to you, and you will be smart. You will choose the volume of solid equals to 1. That will make your life much easier. So that's the part you can do on the second step. The third step will be set up equations to solve for the unknowns. So after your second steps, like you can identify the parameters that you don't know. Because again, phase diagram, the whole purpose of the phase diagram is for you to solve all the parameters within the within the picture. You have pretty much you have six components, or you have five because the rate of the air is equal to zero. Pretty much like the phase diagram, you will always have this five unknowns, or this five parameters that you need to solve for. One more time, the volume of water, sorry, the rate of the water, the rate of solid, the volume of air, the volume of water, and volume of solid. You need to find those five parameters. Sometimes it's given to you in the questions. So if that is the case, then your second part of the procedure will take care of it. Then the third part of the procedure now is to set up the equations to the two solve for the remaining unknowns within the picture. And how many equations you need? So how many equations you need? That will be depends on how many unknowns you have. So that's the maximum. That's five unknowns because the volume of air, volume of water, volume of solid, the rate of water, and the rate of solid. There's five parameters that you need to find out. And um, very likely the questions will give you some of the parameters, some of the unknowns, because in practice is like a measurements that is measurements that we can make either in the field or in the lab. So you may take care of the weight of the solid, or you may take care of the volume of the solid. Then you will lock down one or two parameters. Then like whatever being remain, then that is the number of unknowns you need to solve for, which means the number of equations you need to set up. So this procedure number three is the most important one and is the most difficult one. Once you do the third step here correctly, the rest of the problem is just simple algebra. So set up the equations you need your understanding in geotechnical engineering, which means the understanding of lecture one in the soil phases. And when you try to set up the equations, don't forget you have two very good bridges you can use. We talk about in the previous slide, which is the unit range of which is these two equations actually. It can always help you to simplify or to lock down two unknowns, because again those two equations is kind of like a link connecting the volume and the rate. You know one of it, then you can find out the other one. So don't forget you have two equations that being very useful, which is the unit weight of water is equals to the weight of water divided by the uh, volume of water, and also the G sub S is equals to the unit weight of the solid divided by unit weight of water. And you further work on it, and the unit weight of solid pretty much is the weight of solid divided by the weight of water. Sorry, the weight of the solid here. So with those two equations, you may be helpful. So which equations to use depends on the questions. And also some simple equations like the total volumes is equals to the volume of air plus volume of water, and also volume of solid, and also the total weight is equals to the weight of water plus weight of solid, and also equations or definitions such as the water content, the saturations, those could be helpful too. But which ones to use, it depends on the questions, depends on what information is given to you and what being asked. So this equation step number 3 here is the most important one. But once you finish this step, pretty much is what being remained is just simple algebra. So after you find all the remaining unknowns, then you can go back to complete your phase diagram. Because now for the 3 different phases, you know all the parameters. You can quantify all these numbers right there. So pretty much like after you have this phase diagram, then you just solve for what being asked. The problem could ask you the saturations, could ask you the unit weight, could ask you the unit weight, total unit weight, could ask you the water content. So like for example, the water content is the weight of the water divided by the weight of solid. So now the weight of water, and the weight of solid. You just plug in the equations, then you can find the answer. So my advice is when you're solving a phase problems, could be happening in your homework, could be happening in your exams, could be happening in your EIT exams. This type of problem is very popular in FE exams. So pretty much, I guarantee you will see this again over and over. So that's why it's so important to get it right at the beginning by starting doing the homework, doing it right, and then uh, your midterm exams. I guarantee you have a problem on phase problems, and also your final exams. And after you leave Cal State area, or hopefully you will pass your PE before your graduations. But anyways, like the public exams that are very important for your career. They is also have this a phase relations problems. And it's very important, we all understand this and do right at the beginning. So my only advice for solving this type of problem is never, never, never try to start from never try to start from solving a problem from picking the right equations or formulas. It's not about plugging in the formula, but understanding how the phase relationship work, which start from the phase diagram. Okay, so let's try to solve for one examples. Actually, I have 2 examples here. So examples number 1, let's try to work on this. So again, the question said you have a sample of sand within a mold that is 40 cubic inches. So the volume is equals to 40 cubic inches, and then you took 2.8 pounds of wet sand. So you have a volumes. You fill up the volume with wet sand, 2.8 pounds, and you take out the sand and put it in the oven and you dry it. You get 2.41 pounds, and you assume the G sub S, the specific gravity, is 2.65, and then now ask you to solve for all these parameters right here. So when we see a phase, again, when we see a phase relations problems, don't try to find the equations, but what is the first step again? Drawing the phase diagram. So this is the air, this is the water, and this is the solid. So the first step, just draw the diagram. And second step you would do is fill in the information that is given. So we have the volumes, and we have the weight. It is given that the total volume is 40 cubic feet. cubic inch. So we have 40 right there. The volume is cubic inch, and then the weight is pounds. Don't forget about the units. Always put down the units. It helps you a lot. Take your time and make sure everything is well organized. Don't forget about the details. Being a geotechnical engineer is very important. Pay attention to all the details. Okay, the second part of the questions tells you it took 2.8 pounds of red sands. So which telling me the total weight is 2.8 pounds. And the dry weight is 2.41. We know the G sub S is 2.65. And pretty much with that, we finish the second step. Oh, meanwhile, it's like we know the weight of the air is 0, and this questions, well, remember, on the second step, the other thing we can think about is the saturations, and also whether you can assume the volume of solid equals to 1. And in this case, since the volume is given, so you have a fixed volume, then you cannot assume the volume of solid equals to 1. You cannot do that. Sometimes you can, sometimes you cannot. When the volume is fixed, you cannot do that. And also, you need to think about whether your volume of air is equal to 0 or not. This case, they did not. They did not tell you. They did not tell you the samples is fully saturated. So you cannot do it because there's no saturations informations. So you cannot do this as well, which means you need to find it instead of assume it equal to 0. So from this phase diagram, you have you have 4 unknowns: 1, 2, 3, 4. So you don't know the volume of air, you don't know the volume of water, you don't know volume of solid, and also you don't know the rate of the water. So which means you need to set up move to the procedure number 3, which means you need to set up 4 equations. You need 4 equations to solve for 4 unknowns. Well, in fact, some of them is very obvious. You don't need you don't need spend a lot of time to think about how to solve for the unknown, because for example, the weight of water is very obvious. So equations number 1 you can think of now is the total weight is equals to the weight of water plus the weight of solid. So the total weight is 2.8 pounds, and the weight of the water is unknown, and the weight of solids is 2.41 pounds. So pretty much you can solve for the weight of the water vary, which is equals to 0.39 pounds. And then next, so this is the equations number 1. So the next equations you can think of is remember when it comes to step number 3, always start from the 2 equations that always help you, which is the unit weight of the water and also the specific weight of a solid. You always know the unit weight of the water is the weight of water divided by the volume of water. And the unit weight of water is equals to 62.4 pounds per cubic feet. So with this, we can solve for the volume of water. Now will be equals to the weight of water, which is 0.39 pounds, divided by 62.4 pound per cubic feet. So don't lose track with your units. Don't lose track with your units. So with this, if I take out my calculator, then we can find out my volume of water is 0.00625 cubic feet. Or like, we can state everything in feet, but like we change our order units into feet at the beginning. That will make our life much easier. So 40 cubic inch will be equals to 0.0231 cubic feet. So we've also found out the volume of the water. And then, so this is equation 2 that we use. And the third equations we can use, again, think about the G sub S. So the G sub S times the G sub S equals to the unit weight of solid divided by the unit weight of water. So the unit weight of solid equals G sub S times gamma W, and the unit weight of solid equals the weight of solid divided by the volume of solid is equals to G sub S times gamma W. And what we try to solve for now is the volume of solid. So that will be equals to weight of solid divided by G sub S times gamma W. That will be equals to 2.41 pounds divided by 2.65 and then times 62.4 pound per cubic feet. And if we do our math, this will be equals to 0.0146 cubic feet. So we can find out the volume of solid too, which is equals to 0.0146. And this is I would say this is the equation 3 that we use. And finally, we want to solve for the volume of air. And volume of air will be equals to the total volume minus the volume of water minus the volume of solid. So we have our equations number 4. And the total volume is equals to 440 cubic inch, which is equals to 0.0231 cubic feet minus the 2 that we just found out previously. And the volume of air eventually is equals to 0.0022 cubic feet. So we also find out the volume of air. So with that, we finished our procedure number 4, completing the phase diagram. So this is the phase diagram that we have. And I highly recommend you try to solve this problem by yourself too. Try to solve this problem by yourself too. So with this complete phase diagram, then we can start to solve for the problem they asked for. So first, we ask the total unit weight. Maybe let me move this here. So the total unit weight is equals to the weight divided by the volume. And from the phase diagram, we have all the informations. It's 2.8 pounds divided by the total volume is 0.0231 cubic feet.
that will be equals to 121.65 pound per cubic feet. Part B, he asks for the dry unit rate, gamma D. So gamma D is equals to the weight of the solid divided by the total volume. And since we solve for the weight of the solid, which is 2.41, so making our life very easy now. Once you have the completed phase diagram, and divided by the total volume, and then with the 2, we have 104.33 pound per cubic feet. And part C of the problems asks you to solve for the void ratios, which is equals to volume of void divided by the volume of solid. Again, we can find the information on the phase diagram. So volume of void is equals to volume of air, 0.022, plus the volume of water, which is 0.063, and then divided, so the whole thing is cubic feet, and then divided by volume of solid, which is 0.0146 cubic feet. Always don't forget about the units. And then you calculate this, the ratios of the two give you 0.582. That is your void ratios. And part D asks you the porosity. So the porosity equals to the volume of void divided by the total volume. So you should know this like by heart now. Like, what does it mean by void ratios? What does it mean by porosity? And the volume of void, one more times, is 0.0022 plus 0.0063 cubic feet. And then the total volume is 0.0231 cubic feet. And then this will be equals to 0.368. You can also like solve this problem by using the equations that we developed early on, which is the porosity equals to the void ratios divided by 1 plus the void ratios. So back to a couple slides ago, we have devised the equations. Okay, step number E, he asks for the water content. So the water content is equals to the weight of water divided by the weight of the solid. And the weight of the water is 0.39 pounds, and weight of the solid is 2.41 pounds. And don't forget about this percentage. And you do your math. This will be equals to 16.2%. And lastly, it asks you for the saturations. Which is equals to the volume of water within the void. So the volume of water is 0.063 cubic feet, and volume of void is 0.0022 plus 0.0063 cubic feet, and then times 100%. And after you did your math, so this is cubic feet, and after you do your math, the saturation is 74.1%. So this solve the problems. And again, like the key is setting up the phase diagram, finding all the unknowns. And after you have correct phase diagram with the correct informations, pretty much you are done. The rest of it is just plug in simple equations. And the exams that are given to you in the midterms and the final exams, once I see you have complete phase diagram with the correct informations, pretty much I give you 90% of the credits already. To me, that's the most important part, setting up the phase diagram correctly. And step number 3 will be the most could be the most complicated one, because sometimes like examples 2 that we'll be working on, sometimes the information given to you in the problems may not be so obvious. Okay, so let's solve for this problem together. Examples number 2. So this problem now gives you the void ratios of soil, which is equals to 0.4, and then it asks you the saturated unit rate. So we said what is the corresponding range of saturated rate? And actually there's a typo. It just asks you what is the saturated unit rate. Because I didn't give you the range of the void ratio. I just give you one more ratios. So we will ask you one particular saturated unit rate. So to solve a problem like this, again, the first step to what we to do is to set up the phase diagram. So we have the air, we have the water, and we have the solid. And we have the volumes, and we have the weight. The second step will be filling the required informations. So first, it asks you um, the saturated unit rate, right? It's a saturated unit rate. So pretty much we want to find out the unit rate when the soil samples given here is saturated. So when we know that the samples is saturated, which means we can assume we know that actually it's a fact. The volume of the air is equal to 0. The rate of the air is always equal to 0. So we are at step number 2 now, try to fill in the information that we know. So we know the rate of the air is equal to 0, and also we know that since the specimen is saturated, so the volume of air is equal to 0. And also realize that for this particular problems, the volume is not given, which means you'll be up to us to assume the ratio, because everything is proportion. So we can assume the rate of the volume of the solid is equals to 1, and we can assume the units too. We can assume it to be 1 cubic feet. We can assume this is equal to 1 cubic feet. So now this is all the information we have. We also know the G sub S is equals to 2.65, and we always know the unit weight of the water. So we can take advantage of those two pieces of information, which is equals to 62.4 pound per cubic feet. Okay, so that's all the informations we have. So we finished a step number 2 now. And then we go to step number 3 to set up the equations to solve for the unknowns that being remains. So on step number 3, so this is step 1 and step 2. And step number 3 is set up the equations. And we need 3 equations because we have 3 unknowns to solve for. What we don't know is the volume of water, the weight of water, and the weight of the solid. So remember, when you think of those equations, you need every time the problem change, the way you do it will be a little bit different. It's not every time you follow this cookbook procedure. I mean not procedure, there's equations you must follow. Then you can find the answer. No, it's not that way. It's based on what we have now. Now, we have we have the void ratios. So when we look at the equations that we need to solve for, and what being given now is we know the void ratios, which is equals to 0.4, and the void ratios is the volume of void divided by the volume of solid. And we know that the volume of solid is equals to 1. So which means so this is equations number 1 that you use. We can solve for the volume of a void is equals to 0.4 cubic feet. And we know that the volume of void is equal to volume of air plus volume of water. And we know that the volume of air is equal to 0 because this is saturated. So pretty much we solve that the volume of water is equals to 0.4 cubic feet. So we find volume of water is equal to 0.4 cubic feet. So we know the volume of water. The weight of water will now become very obvious because we know that the unit weight of water always being helpful. You know the unit weight of water is the weight of water divided by the volume of water. So the weight of water will be equals to 62.4 pound per cubic feet times the volume of water, which is 0.4 cubic feet. We do our math, then the weight of water will be equals to 24.96 pounds. So the weight of the water is about 25 pounds right there. This was the equations 2 that we use. And equation 3 will be always like obvious, just like the previous questions that we use. Make use of take advantage of G sub S. So the G sub S times gamma W will be equals to the weight of the solid divided by the volume of solid. This is the equation 3 that we can use, and we are looking for the weight of the solid. So the weight of solid will be equals to the G sub S times gamma W times V sub S, which is equals to 2.65 times 62.4 pound per cubic feet times the volume of solid, which is 1 cubic feet. And we do our math here. The weight of the solid will be equals to 165.36 pounds. So we solve for this too. So V sub S will be, sorry, this is not V, this is the weight. Oops. So this is the weight of the water, and the weight of the solid will be equals to 165 pounds. Roughly about 165 pounds. So then we finish step number 4. We have complete the phase diagram. And the very last part is just to solve. Now we are ready to answer the questions. So they ask you to saturate the unit weight, which means the total weight at the end of the day. And the total weight will be equals to the total unit weight will be equals to total weight divided by the total volumes. So which is equals to the 25 pounds plus the 165 pounds divided by the total volume, which is the 0 cubic feet from the air, and then from the water, volume of water, and also the volume of solid, which is 1. This is 1 here. We plug in all these equations. we got 135.94 pound per cubic feet. So that will be the total saturated unit weight. So this is the example for the second, the answer for the examples number 2. So with the end of this, we conclude the lecture number 1. If you have any questions, please come to my office hour and send me an email.